With that, I'll shut up, and Joe, it's yours.
And thanks very much for the opportunity to be here. So I'm going to talk to you about loop currents and predictability. And like Bob just said, the big deal with the loop current is that it's been a thorn in our side for a long time. Many very smart people have looked at the problem, and we still don't know what the answer is. We don't know how to predict the loop current. And so I'm going to use some, what we might call nonlinear dynamical systems theory, which is a big word for we're going to look at it in a different way than we traditionally look at it, oceanography problems. And we're going to see if we can learn anything. So this work, really, Vitaly Sheremet was my advisor way back when I did my PhD. And actually, this is when we started working this problem. We've been continually working it. So NSF funded us originally to do this, and I have another NSF grant to follow on top of that and that work. And so that's what myself and Carrie McMahon, who's my graduate student, are doing right now at the University of Delaware. The preliminary set of experiments were run at the Graduate School of Oceanography in Rhode Island. We did a little bit of work in the GFD lab at Woods Hole, and then my lab in Delaware is where we're currently doing things. Most of the funding for this came from the National Science Foundation. A little bit got splattered in there from the Texas General Land Office. And so the question is, what does the Gulf of Mexico have in common with a teapot? Any ideas? Like anything? Okay, they're both big masses of slightly warm water. You can maybe tip over the teapot and look at it. But it turns out that there is some fundamental things that you experience every day when you use a teapot or pour a gallon of milk or something like that have some interesting fluid dynamic phenomena that we're going to apply to this larger system. So for right now, we can think of what happens when we pour a teapot is we tilt it. The inertia causes the flow to move out of the spout of the teapot, and that inertia is being balanced by friction, the boundary layer of the friction of the wall. We have a similar situation in the Gulf of Mexico. So you guys all know what the Gulf of Mexico looks like, but I still like to put the figure up here. So we have this big loop current. It flows in. This is an example of a loop current state where we have a loop and an eddy shed off. It also has times when it's leaping in, and the big question is, when is it going to be looping and shedding eddies versus when is it going to be not looping and just leaping across the gap? And we care about this for a number of reasons. One of the big reasons is hurricane intensity is largely affected by the presence of the loop current. Hurricane Katrina in particular got a big boost of energy, all that warm water that fueled growth of Hurricane Katrina and led to that disaster. But I don't want to only talk about the Gulf of Mexico, because we could also look at George's Bank. So this is George's Bank right here. It's Cape Cod out here. This is Brown's Bank, and this is a Scotian shelf. What happens in this case is we have another boundary current. There's a shelf break jet that forms. This shelf break jet has to interact with the northeast channel of the Gulf of Maine. And observations suggest that sometimes the current, or most commonly, the current kind of just flows in and circulates around George's Bank, but sometimes there are crossover events that happen. So again, we have this competition of flow inertia with something else. So if you're a fisheries scientist person and you cared a lot about, say, the population dynamics on George's Bank, it turns out this is a relatively important process. It's not a normal thing, but there are times when you have direct transport between the two banks, which can be important. And also, the initial flavor of this money was for the South China Sea. So we have Taiwan, the Philippines. The Kuroshio current forms, creates a western boundary current. That western boundary current interacts with the Luzon Strait, which is a gap in the boundary, and it forms a loop current or doesn't form a loop current. So we're going to talk a lot about the Gulf of Mexico, but really this is a generic oceanographic problem where we have inertia competing with something. So now back to our teapot, and I always like to use my son as an example. So he wants to pour milk in his cereal in the morning. So he picks up this big gallon of milk and he pours it. but he's still young. He's 7, 8 years old, so he has to pour it really slowly. And what happens? It spills all over. It dribbles down the edge, right? Now I can pick up the exact same gallon of milk. I can pour it at the exact same angle, but when I do it, it's pouring out nicely. So what's happening here is a phenomenon known as the Coanda effect or the Teapot effect. And what we have is the inertia of the fluid is interacting with viscosity. And when I bring it to the same state quickly, it pours nicely. If I bring it slowly, inertia can't overcome viscosity as nicely, and I get this example of multiple states. Everything's the same, but when my son does it, it's dribbling. When I do it, it's pouring nicely. We've all experienced this. Now, what I'm going to try to convince you over the next 45 minutes or so is that the exact same thing can happen in loop current systems. And not just the loop current, but the South China Sea, Georges Bank, and any other number of oceanographic systems. And it's just an example, again, South China Sea. These are subsurface temperature contours, simply showing what we all know happens in the Gulf of Mexico as well. You have times when you have a loop current state, and you have times when you have a leaping state. Just like when we're pouring our teapot, we can have multiple states. Now there's a detail about these multiple states that I'll get to in a second. And just like we do in the Gulf of Mexico, there's a number of works in the South China Sea. It's the same question. What determines transition between states? When is an eddy going to shed? Why does it shed? How long is it going to take for the eddy to shed? When's the next eddy going to shed? It's universal. Everywhere you go and you look at these types of problems where you have inertia, strong currents interacting with, in this case, vorticity constraints, it's an open question. So this is a generic oceanographic question, and we decided we were going to answer this. So Vitaly Sheremet had originally done a little bit of this work, and Glenn Eyerly was even my academic grandpa, his PhD advisor. So going that far back, and that was where this actually really got started. And so observations are expensive, and I was a poor graduate student, and people have done observations and still don't know the answer. Modeling is a wonderful tool, but again, we've used models and we still don't get the right answer, and we've used it for a long time. And so we ended up taking an experimental approach. So when I say experiment, I also mean experiment coupled with theory. So we are going to run experiments, and we're going to build these experiments off of this initial work that Vitaly Sheremet did, 2001 JPO paper. We have a very idealized setup. There's a one grid cell boundary here, and there's a gap in that boundary. Vitaly had prescribed what you call a Monk profile boundary current. Don't worry about it. He prescribed something that looked like a geophysical boundary current. And he asked the question, as I vary my boundary current, the strength of my boundary current, what happens to transitions? And he observed multiple states in his numerical results. Now, the trick here was the reviewers were not very pleased with that because we have a separation problem. And if you do fluid dynamics, separation problems are notoriously difficult. The other half of my work is hypersonic aerodynamics. And even in those cases, we run models and we just can't get the separation problem right either. Separation is notoriously difficult. So people were very skeptical of this result. So we went to a rotating table. So this is the rotating table. It's a 1 meter rotating table at the University of Rhode Island. I just want to put this in there so you can kind of see what's going on. We simply have a big tank of water. We spin it. We spin it to simulate the rotation rate of the Earth. We put a sloping bottom in it to simulate a beta effect. So we can get first order quasi-geostrophic dynamics in our small rotating table. And just because I like to brag a little bit, this is my new rotating table, which is 50% bigger than my advisor's rotating table. It's prettier too, so anyways. So this is what I'm working on right now. Carrie McMahon and I are running experiments here. We have a PIV system that just arrived, so I'm very excited to be running this set of experiments. But let's talk about what actually we did. Okay, so this is a schematic of the tank I just showed you. We did a square tank and a circular tank. We'll talk about the circular tank. So a cylindrical tank. We cut it in half with a sponge barrier. We have an active side that has a sloping bottom. So if you have a sloping bottom and a rotating fluid, you have a parabolic surface. And a sloping bottom gives you depth contours that look like this. So these solid lines are depth contours. And think back, even if you don't like PO, you can remember that flow likes to follow constant depth contours, right? Okay, we can remember that. And we drive the flow. We might remember our large-scale ocean circulation, sphere drip interior flows. We drive the flow by pumping from one forcing basin into the other forcing basin. This creates a pressure difference that percolates through the sponge, and we actually get a fairly broad, uniform sphere drip interior flow. That flow wants to follow the geostrophic contours. It runs into the boundary, forms a boundary current, and then that current travels down and interacts with the gap. So that's what we're looking at. We use dye release as well as a particle image velocimetry system to observe the flow patterns. Just details. So the first thing you're doing when you're running an experiment is I'm claiming that I can take my little 1 meter rotating table and say it has something to do with the ocean, and you should very reasonably be skeptical of that. So my goal is to simulate a quasi-geostrophic dynamical system. So what I can do is I can look at my boundary current that's forming and see how it compares to QG theory. So when it comes to QG theory of barotropic boundary currents, there's quite a lot out there. There's analytic formulations, there's inviscid formulations, and then we wrote a little numerical model to actually solve these things. So if you go back into your GFD text, you'll find a Monk boundary layer, inertial boundary layer, and the other one's Stommel, I think. And these three different competing mechanisms form a generic quasi-geostrophic boundary current. And so at the end of the day, this is for a particular rotation rate of our table. This is the distance, cross stream distance, so basically away from our boundary. And this is the velocity. And we see that the theoretical results are the lines, the theoretical and computational, and our experimental data points are in very good agreement. So I do have something that looks like quasi-geostrophic dynamics in my table, so it is at least a worthwhile thing to study when we think about the real ocean. Idealized, but same governing equations, more or less. And here's the real key. Now this is the very, very interesting thing. So let's say we start down here. So what I'm showing here is different flow patterns. These are dye streaks. We have a low flow rate here. This is all for a rotation rate of 1 radian a second of our table, so that sets all the Coriolis type terms. I'm going to vary the flow rate. I'm going to start low, so inertia is weak. So when inertia is weak, I expect the flow to want to follow geostrophic contours. My boundary current forms. It separates from the boundary. It wants to follow geostrophic contours, so it turns in, forms a loop current before traveling back out. And of course, we got to satisfy something that looks like continuity, so it's got to come out the other end eventually. I'm going to increase the flow rate, and I see that the inertia is carrying it farther and farther across the gap. And eventually, I increase the flow rate so much that this eddy pinches off, and I'm in a leaping state. So I was in a loop current state. By varying the inertia of the current, I ended up in a leaping state. Now here's the cool thing. When I start in my leaping state and I decrease the inertia of the current, I continue leaping, I continue leaping, I continue leaping, and not till I get down to a low flow rate do I transition back. So this is what's known as hysteresis. So increasing flow rates have different patterns than decreasing flow rates. This was the first time anyone had shown that the interactions of inertia, the nonlinear terms in our Navier-Stokes equation, competing with vorticity constraints, our kind of, F term in our equations, could lead to multiple states. So think about the implications for that if you're trying to predict something in the ocean. I know everything I can know about the system at a given time here. I know the flow rate, the viscosity, I know everything, and I still couldn't tell you if I'm going to be in a loop current state or a leaping state, which is pretty interesting. I mean, that was pretty cool. And so we ran this set of experiments, and it has big implications for how we would study the loop current. When we talk about transition prediction, a lot of loop current science will analyze satellite altimetry, and do linear statistical analysis. A linear statistical analysis does not account for multiple states. So that's kind of an important thing. And so we want to understand this. It's one thing to show it, but we want to understand it. So we ran some numerics. We see the exact same thing in the numerics. So it's not like this is either some crazy experimental result or some crazy numerical result. It all comes together. We are seeing this as a robust feature both numerically and experimentally. And I should say, in the South China Sea, some people have run large-scale ocean models, and they see indications of multiple states in the South China Sea as well. So we're in a parameter space that is actually relevant to the ocean. There's been a number of Chinese scientists who have studied this in the South China Sea. So this isn't completely crazy. This is just some flow patterns. These are the examples of some of the PIV data, so I get vector fields. This showing the hysteresis. If you're a fisheries person, this is actually kind of interesting. So off of Taiwan, when the South China Sea loop current is getting ready to spin off an eddy, there's something called, so as this is getting ready to spin off, there's a separation. This would be basically on the southern part of Taiwan, and it creates this upwelling. And all the local fishermen know all about this because that's some of their best fishing comes right before the South China Sea loop current is going to transition. So this is actually an indication of transition from a looping state to a leaping state in the South China Sea, which is kind of a neat thing. But let's take this one step farther. I showed you data when I was rotating my table at 1 radian a second. I reduced the rotation rate and I increased the rotation rate. What you're seeing here is this is the state of the system, or how far into the gap the loop is penetrating. So this is a loop current state, this is a leaping state, this is this region of hysteresis, where there are multiple states. And I see that the region of hysteresis increases with increasing rotation rate and decreases with decreasing rotation rate. So we have all these hysteresis curves, and we can stack them all together, and we see something that looks like this. So we can understand what this figure is telling us. The state of the system is our z-axis here. So the system lives on this surface. These would be loop current states. These would be leaping states. This surface lives in a parameter space, which has to do with the inertia of our current and the rotation rate of our current. So we can actually understand the dynamics of the loop current by tracing the evolution of our system on this surface. As we, say, start here at some rotation rate, as we increase the flow rate, we move this way. Eventually, we fall off the edge. That's a transition between states, and now we're on the lower surface. We can move back as we decrease it, and we pop back up, transition the other way. In the lab, every time we saw a transition that happened by falling on or off of this, an eddy shedding event occurred. Just a one discrete eddy shedding event. Now, if you look at satellite data, you might say, well, yeah, but I know I can go look at years worth of satellite data, and I find times when we go from a retracted state to a penetrating state to a retracted state or vice versa, and there's no eddy shedding event. Well, you can account for that. If you were to, say, vary your parameters in a way that you were to go down and around, there's something called a cusp point right here, which I'll get to in a second. You can actually go around these drop-offs and transition smoothly between states with no eddy shedding event. So this provides a framework that we can at least start to understand some of the dynamics going on. If you project this thing down, so that actually is called, if the math talk of that is called a cusp catastrophe. There is a branch of mathematics that's fairly obscure known as catastrophe theory, which I know absolutely nothing about other than I was in a used bookstore that had a science shelf about this big, and there was a $4 book called Catastrophe Theory. And I bought it, and I started reading it, and I started reading about something called a cusp catastrophe. And I thought, that looks a heck of a lot like what I'm doing in my lab. And we've published a number of papers on the cusp catastrophe interpretation of the loop current. So we can take that catastrophe surface, is just the name of it, and we can project those folds down. So these folds are the important part. They're where transitions occur. And I can understand that in my high flow rate, low inertia case, I have leaping states. I have loop current states in the low inertia, high rotation rate case. I have the region of hysteresis, and then I have the region where these folds no longer exist and I can go around and have no catastrophe where I fall off the edge. So I can start to look at my loop current observations in a way that explains eddy shedding states when they may or may not occur if I was able to track the parameters of the system. So this is getting a little bit out there in the weeds of crazy math that I don't understand very well. But there's a really nice way of thinking about this whole system, and it's called Zeeman's catastrophe machine. So you could all do this when you go home for homework. Take a cardboard circle and pin it to the wall so it can rotate. Along the axis, attach a rubber band somewhere along the axis to the edge of the circle. Take a second rubber band, attach it to the edge of the circle, and bring it, and that's your point P, which you're going to move around on. So this is a system that illustrates a cusp catastrophe. Now you could go back to an undergraduate physics textbook and you could write down, well, this is a spring, a rubber band that acts like a spring. I could write down Hooke's law. This is another rubber band that acts like a spring. I could write down Hooke's law again. And with Hooke's law, springs, I can define a potential function. So you can write a fourth order potential function, right? Fourth order, something looks like this, a potential function. So when we think about potential functions, the stable states like to hang out in minimas. So a fourth order potential function can have two stable minimas. Now if you were to take and move this point around and track the angle of your disk, this is exactly what you'd see. When you're in, so if we move it around up here, our fourth order potential only has one minima and we only have one state. When we move it down below a certain distance, our fourth order potential shifts and it has two possible states. When I'm over here, we have one deep well and one well that's not a minima. And so we have one solution. However, as we start to move across, we can see a second minima forms before we transition to this other minima. So in this region here, this is that bifurcation set I was talking about in the last figure. This fourth order potential function tells us there will be two minimas here. And how we move back and forth with hysteresis is by moving from one minima, it starts, so you're in this minima, you start to move across, that goes away, you plop yourself over here, right? So now we're over here. Now we could move ourselves back in the other direction. We would move back into this double potential well case, but you'd be on this side. So this is actually a geometric way you can understand this whole cusp catastrophe thing, and something that I actually did this for fun on the wall of my office, my old office. I don't have it anymore. But you can trace out this potential function. So this is actually quite interesting because it leads us to assume if we were very, very clever, somewhere in the dynamics of loop current systems, there is embedded a fourth order type potential function. Now that's kind of an empirical fit, but somewhere in loop current dynamics, there should exist a fourth order potential function. And if we could figure out that fourth order potential function, it would dramatically increase our ability to predict the loop current. And actually that's what I'm funded to do right now. So they funded me to do work to try to see if I can identify a fourth order potential function in our nonlinear quasi-geostrophic dynamics. That's an awfully lofty goal, which may or may not happen, but that's what I'm trying to do. But let's say, okay, that's all great. And so that's one of the main takeaways of this work, that if we take a different view than our traditional oceanographic view, in this case, we took a view of nonlinear dynamical systems theory. It gave us a different framework that we can interpret our data in. Now, this isn't just fluid dynamics. If you go into nonlinear dynamical systems theory, there's a lot of population dynamics work, there's a lot of predator-prey relationship works. Anything that has some nonlinear interactions, you can write these relatively simple models and get some very interesting and complex results out of. Okay, so let's take this and try to make it a little bit closer to the real ocean. Let's add stratification. So barotropic is nice, let's add baroclinic effects. We basically converted ourselves to a square tank, same basic setup, geostrophic contours, boundary current form interacts with the gap. However, this time we have a two-layer fluid. Again, we can verify that our boundary currents are approximately two-layer geostrophic. Of course, if you want to go two-layer geostrophic, there's not as much theory out there. And actually, we had to go all the way back to 1955 and look at some work that Charney did to get a structure function for a two-layer western boundary current. And it turns out when you go through the math of it, we get pretty darn good agreement. It was a little bit surprising we had to go all the way back for such a fundamental problem. And at the end of the day, I'll cut through all of the boring stuff and say, when we have a two-layer system, I appropriately non-dimensionalize things. I have one non-dimensional coefficient that's related to flow inertia, one non-dimensional coefficient that's related to these vorticity constraints. You want to conserve your potential vorticity. And we see again this Cusp Catastrophe. This is the bifurcation set of a Cusp Catastrophe. Since we have a two-layer flow, we no longer have north-south invariance. So that means something that's flowing from the north behaves differently than something that's flowing to the south. However, in both cases, we have multiple states, hysteresis, and this Cusp Catastrophe. I'll talk about what these little lines are in a minute. So we should probably put some math to this. I mean, this is all nice and pretty, but we should actually actually try to back it up with some actual physics. So we did what we like to do in physical oceanography and fluid dynamics. We went back to our shallow water equations. So this is a barotropic flow right now. We could also do it for a two-layer baroclinic system. And we get our vorticity equation. And what we want to do is we want to analyze our vorticity equation in the different parameter spaces that we're working in. So we can take that vorticity advection diffusion equation. We can scale it for the steady flow low inertia, for the time-dependent low inertia, and for the steady flow high inertia case. We're going to look at all those different cases and work out what the fundamental balances should be. So this is your PO classes where they make you write out the equation, start crossing off terms, and analyzing what's left over. So for the steady low inertia case, this is a loop current. This is a looping state. We can write the first order nonlinear terms in terms of the stream function are these. And then we have, these are basically our topographic beta effect. In the lab, we have a topographic beta effect instead of a planetary beta effect. And here we actually have Ekman dissipation. And so there's something called a beta plume solution that has been well known for quite a long time. Interestingly, we found two new analytic solutions. So there's a GRL paper where we basically crossed off the nonlinear terms. This looks a lot like a heat equation. It turns out if you look at topographies like this, so this is basically a straight slope, that's alpha x, and then the y direction is our downstream distance. So we have a slope that if gamma there is equal to 0, it's just a constant straight slope, or that slope can be varying up or down by setting parameter gamma here. So this is just a generic slope topography. Crossing out the nonlinear terms, you can actually solve this analytically, and you get an error function solution. So if you're a mathy type person, you can introduce a similarity variable, and you can derive an analytic similarity solution. The really cool thing, and it actually just got accepted a couple weeks ago, is we added in the nonlinear terms, and you can also analytically solve it. So there ain't a lot of analytic nonlinear solutions out there. But we could do this. Again, you introduce a similarity variable. Again, mathematical details maybe you probably don't care about. And you get a solution for this crazy thing called a Lambert W function. I had no idea what a Lambert W function was until we started working this problem. But it's really interesting that you can actually get a nonlinear analytic solution for this set of equations. Although in this case we had to assume cubically varying topography, which you might say is really restrictive, but if you're interested in climate dynamics, you might go and look at the Norwegian coast. And on the Norwegian coast, there's a slope current that likes to shed eddies that spin off into the, whatever the sea up there is. And this is thought to be responsible for a lot of deep water formation. If you analyze the topography where the eddies shed, it's cubic, which is really kind of cool. So that's actually something we're trying to look more into. But just know, so for the steady loop current case, we're in a beta plume solution, and we have some analytical work done there. This is just kind of a nice side note. Actually, if you look at the Gulf of Mexico, this was the GISR mooring array. So this is the BP oil spill was here. And it actually turns out the topography from here to here also satisfies those analytic solutions. Now they're barotropic. We're working on making them baroclinic, but it's just kind of a nice little side note. Let's get back to the next case. Okay, so we had low inertia steady. We got some analytic solutions. They tell us how the loop current state kind of spreads. Let's add dissipation. So if you go back and if you study the loop current, you might have come across some work by Nof, or Pichevin and Nof. And they have these papers called the momentum imbalance paradox and the eddy cannon. And it was this interesting solution where these periodic eddies were shed off of something that might look like flow around Cuba. It turns out, and we didn't know this when we did it, but we basically reproduced their results, but we added friction. So what we do is we assume, so this is the time-dependent case, so we didn't cross out our time derivative of vorticity. And we have our dissipation terms here, and you can look at an Ekman decay time scale for a geostrophic current. So don't worry about all that. The key takeaway is this, and this is another thing that could potentially be very important for a loop current in the Gulf of Mexico. We're plotting here, this is the transport, basically the inertia of the current on this axis. This is for baroclinic flow, this is for barotropic flows. And what I'm plotting is the ratio of the advective time scale to the Ekman dissipation time scale. So how fast are we advecting vorticity into the loop current versus how fast we're taking it out? So the really interesting thing here is when we're advecting more vorticity into the loop current than we're dissipating, that means we're above 1, we do find a periodic eddy shedding state. So Pichevin and Nof proposed a periodic eddy shedding state. Every time you read a satellite paper on the loop current, they always refer to a periodic eddy shedding state. There was no evidence that a periodic eddy shedding state even existed. In our lab, in this special case where you have more advection than dissipation of vorticity, all that excess vorticity has to go somewhere. It's just going to accumulate, and how it accumulates in our lab is it sheds eddies. And so this is a different mechanism for loop current eddy shedding than I talked about with the transition falling off the bifurcation set. So you can have periodic eddy shedding states, and you can have discrete transitions. So not all loop current eddy shedding events are the same. There's, at least in our lab, there's at least 2 different fundamental mechanisms that can result in an eddy shedding event. One of those is periodic, and one of those has to do with parameter changes. And so the barotropic, you can do this for barotropic and baroclinic, you get the same result. When advection is less than dissipation, you have a steady loop current state. So this tells us that dissipation is very important to understanding what's going on in the loop current. And if you really think about it, dissipation is the one thing we've done a horrible job of measuring and understanding. I don't think we have the observations out there. So I'm hopeful that we will learn something about dissipation in the next 10 years of loop current science. And so the last thing is we can do our traditional high inertia, steady flow. Basically, we're assuming that these nonlinear terms are big, so they're bigger than the dissipation. We're going to cross a lot of this off, and we're going to look at a potential vorticity conserving jet. So one of my favorite GFD books is Cushman-Rosson's old book, the one that's like this thick. It's a great book. And he does something clever in that book where he says you can take a jet, and so this is my vorticity. You can break it into a curvature. So this is how the jet's curving, like a loop current curvature of a jet, and cross-stream shear. So there's a shear component and a curvature component. So we just write out, this is simply potential vorticity conservation, where we broke it into cross-stream shear and curvature, and then we have a interfacial term and a beta term. And we propose the following critical transition conditions. So when we have a leaping state, at what point does that leaping state, at what inertia does that leaping state transition? When does it fall off the bifurcation set? And we say that, well, what makes sense? The curvature should be about equal to the radius of our eddy should fit inside the gap, right? Makes sense. So when you do that, you simply say, well, I assume that when the radius of curvature is equal to the gap half width, and you solve for v. And it tells you what the velocity should be at the critical transition condition. And there's some extra noise over here from interfaces that I'll talk about in a second. And so since we had a PIV system in our lab, we could actually measure directly curvature and cross-stream shear, so we could measure all of these terms explicitly in our laboratory experiment. And this is the lower, I recast the bifurcation set in terms of velocity and rotation rate. So this is that lower edge of our bifurcation set. The downward pointing triangles are our experimental observations, and this line is what we got from the theory. So a potential vorticity conserving jet with this condition that it's going to shed an eddy when the eddy fits inside the gap agrees really, 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 really well with our theoretical results. And of course, this little blurb here, this has to do with the interface displacement. If you have a two-layer system and you have a boundary current, you have kind of high pressure near the high or low pressure near the boundary. And so that's going to cause your two-layer, your layer interface to be deflected quite a bit. When you leave the boundary, there's nothing supporting that pressure gradient, and so that interface is going to relax a little bit. And so you can actually formulate this in terms of basically an additional stretching. If you think about potential vorticity conservation, this is an additional stretching term that comes from interface rebound. We couldn't directly measure this. I actually can measure it now. At the time, we couldn't measure it. So we ran a couple different interface rebounds. So given the initial deflection of the interface, we're going to allow it to rebound. And we showed that the trends are consistent with our experimental data. This is the purely no interface rebound, and this is, I think, 5, 10, 15, and 20% rebound. And we're seeing things are curving in the right direction for both northward and southward flowing currents. So at least in the laboratory, it would appear that our quasi-geostrophic shallow water equations match with our theory, and we can paint a pretty good picture of some fundamental dynamics of the loop current. And I'm not going to talk about this. It turns out if you just think about, go back to your like intro PO class, and you think about your ice skater spinning around and stretching and squishing, you can just look at a simple idealized picture, and you can get it all out. So if anybody's taking maybe qualifying exams, maybe you'd remember that. And with that, that's really all I wanted to talk about today. I've used up a lot of your time. So this work represented the first evidence that hysteresis in multiple states were a real thing based on the competition between fluid inertia and vorticity constraints. We've also shown that loop current or these types of systems appear to be governed by this global dynamical systems theory Cusp Catastrophe formulation. That doesn't mean it's a useful formulation. It may or may not be, but we do see we can think about it in this global dynamical systems framework, and that might be an insightful framework to look at. We found that I didn't really talk about ocean-relevant parameter spaces, other than I can say you can go to the South China Sea and you can find numerical modeling results that show hysteresis in multiple states for the South China Sea in actual realistic parameter spaces. No one's ever looked at this in the Gulf of Mexico. So that might be something that a modeler could do in the Gulf of Mexico. The original Gulf of Mexico work, the Hurlbut and Thompson work, is really close to this. It's actually, it turns out all the theory that we did is very consistent with their results. And some of their interpretation, it's very close to this in that original work. We also proposed, there's two different mechanisms for shedding an eddy. There's this bifurcation set eddy shedding event, and there is the possibility for a true periodic eddy shedding state as well. So if you're analyzing time series analysis of the loop current, it's important to figure out if this is part of an eddy shedding state or if it's part of a singular eddy shedding event, potentially. And there's this idea that there may be a fourth order potential function buried somewhere in the shallow water equations. And that's the theory work I'm doing right now is basically centered around this. So we're running a new set of laboratory experiments. We're extending the parameter space. We're looking at some more detailed interactions. But the theoretical side of life is looking for a fourth order potential function in the nonlinear shallow water equations. And that's all I got for you. So if there are any questions, concerns, wonders, or worries, I would appreciate them.
So, yeah, maybe I'll start.
Okay.